Hey, everybody. All right, it's 5:30. Whoa, I just had a notification go off on my computer at the same time, so it kind of scared me. All right, it's 5:30, so let's go ahead and get started. All right, so welcome everybody. How's everyone doing today?
Good, Professor. How you doing?
Good, I'm good. I need a haircut. I was supposed to get one this past weekend, but the appointment kind of fell through, and so having long hair for one more week. Yeah, I don't mind the look. It's just it gets really itchy and it gets really warm, especially as the weather kind of heats up, and so I'm looking forward to that. Okay, and so today we're going to be starting a new set of lecture notes, and so this is kind of a kind of almost like the sequel to what we went over last week. And so last week, we went over this this idea of the 1D blood flow equations, which are still fairly complicated, but in kind of in the spectrum of different computational methods, they kind of sit in between LPMs and CFD. And so one of the nice things about 1D equations is that it allows us to study several different phenomena that we haven't really looked at before, right? And so this week we're going to look at something called impedance, which is also going to give us kind of another perspective on the whole wave propagation phenomena. Okay. And so I'll give you some fair warning that that the math is again going to be fairly intense, but again the details of like the derivations, the details of the math are not super important. At least to me they're not super important, but it's really kind of the takeaways and kind of the kind of the conceptual knowledge that you'll get at the end. Okay. And so I'm not sure if this set of lecture notes is going to take us the whole week to do, because I only have about 9 pages in in my PDF. And so I think if we have time end of the lecture on Thursday, and I'll help you out with problem 3 and problem 4 on the homework, because those problems involve something called recursion. And if you've never seen it before, it'll be kind of a very new and kind of strange concept. And if you have seen it before, you probably hate it. And so kind of in both situations, I think we'll benefit from taking a look at it together as a class, and kind of helping you get started with that, because the logic for that is a little bit difficult to understand. Okay. All right. And so besides that, hope you guys are still working on your projects. And so I've heard from actually quite a lot of people in the class. You guys showing me your model, showing me your simulation results, and so so far from what I've seen, it's looking really good. And so you guys are doing really well on the projects. But make sure that if you haven't got started yet, make sure you're getting started on it, and just so that once that deadline of doing the geometry, then that doesn't really sneak up on you. Okay. Okay. And so, are there any questions I can answer before we get started today? Okay. All right. So let's go ahead and get rolling. And so the title of the notes this week is called "The Impedance of Vascular Networks." All right. And so just like, I mentioned, a couple minutes ago, that this is kind of the sequel to the 1D equations. And so, we're going to work with the 1D equations again, and we're going to manipulate it in such a way that, we can study this thing called impedance. Okay. All right. And so let's define impedance first, because I think, that's kind of a relatively new term. And I always spell it wrong, right? And so it should be impedance, not impedance. All right. And so what is impedance? And so, up to this point, we've covered the concept of resistance, right? And so resistance, we've kind of understand it to be kind of the viscous resistance to fluid flow inside of a blood vessel. And so impedance is very similar to that. And so impedance represents kind of a vessel's ability to resist fluid flow or to impede it. Okay? Right. And so in that sense, it is very similar to resistance, but the difference between impedance and resistance is that impedance depends, the value of the impedance depends on the frequency of the flow. Okay. Because in reality, we know that the blood flow in in the cardiovascular system is not constant, right? And so, we know it goes up and it goes down, depending on what the heart is doing at the time, right? Right. And so, the one way that we can say is that, the blood flow is oscillatory, right? And so that means that it just oscillates. Right. And so, just to kind of remind you, we have a flow waveform. So we have Q and we have T. Okay? And so the flow waveform might look something like this, right? And so you can see it's not quite a sine wave, but it's but there's some repeating aspects to it. And so, if we continue on this graph, what you'll see is that this graph will kind of repeat itself, right? Okay. Because every second, your heart is pumping and your heart is kind of pushing out blood from your body just like that. Okay. And so impedance basically says that the amount of resistance or the amount of impedance it's hard to come up. Its synonyms are hard. And so the amount of the amount that your blood vessels will resist the fluid flow will depend on that frequency. Okay. And that's what we have here. And impedance is really important. And so, the fact that your blood vessels can resist certain pulse frequencies depending on the other ones, this actually gives rise to, the wave reflection phenomena. Okay? And so, we've already talked about, the whole wave propagation phenomenon where, every time that your heart pumps, it sends a pressure wave down, the vessel walls, right? And so that's separate from the blood itself because this pressure wave travels along the vessel walls, right? And we've already talked about that. Once that pressure wave hits the capillaries, that wave is going to bounce back and travel up the other way, right? And so that's wave reflection. And so exactly basically, when we had kind of our pulse on a string, right? And so we put the pulse travels down the string, it hits the wall and it reflects coming back. Right? And so that's kind of an extreme situation, but in reality, in the cardiovascular system, you can have wave reflection that occurs in other parts of your cardiovascular tree besides the capillaries, right? And so one aspect or one geometry in particular where this happens is at vessel bifurcations, right? And so remember, bifurcation is nothing more than just, you have a vessel coming in and it splits off into two, okay? Right? And so we have a parent vessel and we have a daughter vessel, right? And so what happens in reality is that, you have a pressure wave coming in, okay? And then once it hits this bifurcation, part of the wave will continue going forward, right? But a small portion of the wave will actually bounce back. And so it's usually not a huge portion, and so it's usually just a small one. But, with all the bifurcations that you have in your body, once you add up all these kind of, micro reflections off all of them, then that's when it becomes really significant. Okay. And the reason we have this, and the reason we have this kind of wave reflection, is that, once you go from one vessel to another one, and so you go from the parent vessels to the daughters, the impedance is actually going to change, right? And so when the impedance changes from one vessel to another one, that causes some of the pressure waves to kind of reflect back. Okay. All right. And so in this unit in particular, we'll be examining, how do we actually quantify this impedance, or how do we find it? In particular, we're going to be doing this for very, very large vascular trees. Okay. And so probably not today, but probably on Thursday, we'll talk about an algorithm where you can take, a very, very complicated vascular tree and then find the total impedance of that entire thing. Okay. And which is kind of exactly what you'll be doing on the homework too. Okay. And so this is really useful because, we can analyze vessels kind of one at a time. But if you kind of remember from the very beginning of class, you have hundreds of thousands of miles of blood vessels in your body, right? And so if you measure things one at a time, you're going to be not having a good day. And in fact, you might not have a very good career too, because you could spend your entire career measuring all single vessels at a time, and you never even get close to finishing. And so we need methods to kind of analyze kind of clusters of vessels as a whole, and say, what's the resistance or what's the impedance of this entire cluster of vessels. And that's what's going to be useful for our calculations. Okay. And so I want you guys to kind of think about that, or kind of keep that in the back of your head as we kind of build up this theory, where, eventually we're going to end up with an algorithm to compute the total impedance from a huge cluster or a huge network of vessels. Okay. But before we get there, we're going to do a lot of math in between, and so it's not going to be pretty, but hopefully it'll be at least semi-interesting. All right. So any questions on this before we move on? Okay. All right. And so where do we begin, right? And so just like we mentioned before, our starting point is going to be the 1D equations. Okay. But we can't work with the 1D equations right away because it's a little bit too complicated. And so we're going to use a mathematical technique called linearization. And so what we're going to do is we're going to take the 1D equations and we're going to linearize them to make them a little bit easier to work with. Right? All right. And so linearization, it's a common tactic in in applied math, because a lot of times these governing equations for these physical phenomenon, think of like Navier-Stokes or something like that. These equations are often way too difficult to work with in order to draw some analytical conclusions, right? And so when we linearize the equation, we basically make it easier to solve by approximating all the nonlinear terms. Okay. And so, because usually, when you're solving these kinds of equations, whether it be an algebraic equation or a differential equation, usually the ones that give you the most headaches to solve are the nonlinear terms. Right? And so let me show you what I mean by nonlinear term, in case you've never heard that term before. Right? And so let me first write down our 1D equations as we kind of derived last week. Okay? Right, and so first we have our conservation of mass. And so conservation of mass, we have partial A, partial T plus partial Q, partial X, okay, is equal to 0. So that's our conservation of mass. Okay. Right. Then we have our conservation momentum. So conservation momentum, we have partial q partial t plus partial z of 4 over 3 q squared over a, okay, plus a over rho partial p partial z, okay, is equal to minus 8 pi nu q over a plus nu partial squared q partial z squared, okay? And I'm going to circle all the terms here that are non-linear. All right, so that one's nonlinear, this one's nonlinear, and also this one is nonlinear, okay? All right, and so what do all these terms here have in common? So, these are these terms are nonlinear because they involve the product or quotient of variables that we want to solve for. And so if you remember, for the 1D equations, we have three variables that we want to solve for in our system, right? And so first of them is the flow rate Q. Okay, next is the local cross-sectional area A, and also the pressure P, okay? And so any term here that has a product of these guys or a quotient of them, that is determined as a nonlinear term, right? And so if you look at the first term, the first thing that I've circled, the partial z 4 over 3 q squared over a. And so there's actually two nonlinearities here. So first of all, we have q squared, right? And so the fact that we have q squared means we have q times q. That means we have a nonlinear term there, right? And then we also divide by a. And so the fact that we divide by a basically means that, we have another nonlinearity there, right? So that first term there is very nonlinear, okay? And so for the second term, we have a divided times partial p partial z. And so again, we have the product of a, which is something that we want to solve for, and p. In this case, it's the derivative of p, but it's kind of the same thing, right? And so that's also a nonlinear term. And then for the last term, we have q divided by a. And so we have the quotient of q and a. And so that makes the term nonlinear. All right. Any questions on this so far? All right. And so, by linearizing this equation, we either want to get rid of those terms, or we want to put them in a simpler form that we can work with a little bit more easily. Okay. And the way that we're going to do that is we're going to define what's called a reference state for the blood vessel. Okay. And so a reference state basically is kind of a state of the vessel where we kind of define all the solution quantities. Okay. And so in particular, we're going to define a reference state where we have a reference flow, a reference pressure, and a reference area. Okay. Okay. And what's common for these kind of situations that we define the reference state to be kind of the mean state or the average state. Okay. And so if we set Q is equal to Q naught, this would be kind of the mean flow rate. Okay. Next we have A, and so we'll define that as A naught. Okay. And so this is going to be the mean area. Okay. right? And then we're gonna have P is equal to P naught, and this is gonna be our mean pressure. Okay. All right. And so by defining this mean state, what we can say is that, we could reformulate our equations to talk about, changes from this mean state. Okay. And if we make the assumption that, if we, once we define this mean state and we make the assumption that changes to this mean state will be relatively small, that will help us simplify or eliminate some of the, a lot of the nonlinear terms. Okay. Right. So I'll be kind of honest with you guys that this process of linearizing the equation is usually a very long and kind of painful process, and so I'm skipping most of the work for that just because it's there's going to be enough math that we're going to talk about in this chapter. But I just want to talk about just kind of in general, what you would do to linearize the equations. So and so I don't want to go from a situation where we go from these equations and all of a sudden by magic we get the equations that we'll get on the next page. And so I want to talk a little bit about how we obtain those equations, but just be aware that I'm skipping a lot of the details in between just because it's one of those things where it's way too easy to get lost in those details, and and the whole point of the lecture is lost at that point. And so just be aware that just by this process of linearization is there's a lot more involved in it, but I'm giving you kind of just the Cliff Notes or the Spark Notes version of it. Okay. Okay. So any questions on this so far? Okay. All right. And so by defining the mean state, we can then say we can linearize the equation around this mean state. Okay. And assume deviations from the mean state are relatively small. Okay. Right, and so this will help us eliminate a lot of the nonlinear terms, or at least put it in a form that's a lot easier to work with. Okay. Right, and we're going to make one more assumption too, just to help us out with the solving. And so we're actually going to take out one of the linear terms too, and we'll assume that the radial viscous term is a lot more significant than the longitudinal one. Okay. And so what this allows us to do is that this basically allows us to eliminate the very last term of the momentum equation. And so this new partial squared q partial z squared, right? Because remember the z direction is the longitudinal one. This basically allows us to eliminate this term from the equation. Okay. All right, and so by doing those main things and by skipping a lot of the math in between, we end up with the following linearized equations. All right, and so first we have our continuity equation, and so our conservation of mass was already linear, and so we didn't have to do anything for that. Okay. All right, so that's fine. Okay, and then we have our momentum equation, and so our momentum equation is simplified quite a bit. Okay. And so we have partial q partial t plus a naught over rho times partial p partial z is equal to minus 8 pi nu q over a naught. Okay. Right. And so these are the linearized 1D equations. Okay. All right. And so, whenever you perform a linearization like this, or any kind of simplification of the equations, you have to ask yourself, where is this going to be valid, or where can we assume this? And so, generally, this particular linearization is valid when the pulse wave speed, the pressure wave speed, is much higher than the blood flow velocity. Which in general is almost always true in the cardiovascular system. And so, we don't really have to worry about that. And so that's, that's good. Okay. All right. And so, unfortunately, we're only, very partially there. Okay. So we still have to work on these equations quite a bit in order to get them to a form that we can work with. Okay. But let me just give you a hint about where we're going. And so basically, what we're going to do is we're going to take these two equations and we're going to kind of work on them. We're going to massage them a bit. And then eventually, we'll be able to get what's called as the classic damped wave equation. Okay. Okay. And so it's called the classic damped wave equations because it has a very classical solution. And so, that's nice because it'll be something that we can kind of easily work with and kind of easily understand from that, right? But in order to get there, we have to do quite a bit more math in order to get that. Okay. But from here on out, hopefully it's at least it should kind of make a bit more sense. Okay. So any questions on this so far? Okay. All right, and so to start this, let's first define the wave speed. And so the wave speed is, exactly as you would think, that's the speed at which the pressure waves propagate down the vessel tree. Okay? And so we're going to define it as a variable called C naught squared, okay? And then we're going to set this equal to A naught divided by rho times partial P partial A, okay? All right. And so the reason we're defining this is because we want to kind of make a substitution into the conservation of mass equation. Okay. And in particular, the term that we want to replace is partial A partial T. Okay. Because right now that's kind of the term that's kind of sticking out a little bit because we want to put everything in terms of pressure and flow. Okay. Right. And so I'm going to do a step here that's going to seem like it's I kind of pulled it out of a hat, But just kind of bear with me for a second, and then you'll kind of see the reason why we do this. Okay? And so let me take partial A, partial T, and then break it up using the chain rule. Okay? And so partial A, partial T is the same as partial A, partial P times partial P, partial T. Okay. Right. And this is significant here because here we have partial A, partial P, and up here we have partial P, partial A, right? And so if we kind of flip that and kind of plug that in here, right? And so we take these terms and kind of plug it in for that. I mean, first of all, we have to solve for that. Then we end up with partial A, partial T is equal to A naught divided by rho CP squared, or rho CO squared, sorry, times partial P, partial T, okay? Great. And so let's take this equation right here and let's plug it into conservation of mass. Okay. And so if we do that, then what we'll do at that point is we'll eliminate A from the equation, right? And so our new conservation of mass expression will look like this. So A naught divided by rho CO squared partial P, partial P, partial T plus partial Q, partial Z, okay? And this is equal to 0, right? Right. And so all we did was we just made a substitution for partial A, partial T, right? And so this term right here used to be partial A, partial T, okay? All right. So any questions on this so far? Yep. So I know it's a lot of math, but it's you know, it's you know, don't get too bogged down in the details all too much. And I know that's really easy for me to say as you know as the instructor for this class. But you know, by the end, you know, you'll kind of see kind of the big picture ideas, and that's what I really want you guys to focus on, right? And so, you know, for these derivations, you know, I'm never going to ask you to do these, recreate these, because I think that's just kind of cruel. But you know, the unfortunate thing is that, you know, in order to get kind of the big picture ideas, we kind of have to dive into the derivation quite a bit. And so I'm you know, kind of trying my best is to kind of highlight just the important points, just so you can kind of see, you know, where and how we obtain, you know, the equation that we do. Okay. All right. So I say that, you know, because we're about to do another kind of strange step. And so what we're going to do is we're going to take this entire equation and take the derivative with respect to Z. Okay. And so we're going to end up with, you know, with quite a big expression there. Right? All right. And so if we do that, then we end up with the following. And so we have A naught divided by rho CO squared. And so all of those stay the same because they're just constants, right? Then we have the cross derivative. And so we have partial squared P, partial Z, partial T, okay, plus partial squared Q, partial Z squared is equal to 0, okay? All right. And believe it or not, you know, this looks like a mess, but this is actually kind of what we want, because what we have here is this term right here, which is the cross derivative of pressure, okay? And so we've taken the derivative in terms of our two kind of main variables here, which is z and t. Because now what we can do is we can take kind of this, take our momentum equation and then try to obtain the same expression here. So we can kind of make a substitution. And so what we want to do is want to try to get partial squared p, partial z, partial t in momentum equation. And make a substitution. All right. And so in order to accomplish that, we're going to take our momentum equation, which already has partial p, partial z, and let's take the derivative with respect to time. Okay. And so that's going to give us partial t of partial q, partial t, plus a naught over rho, partial p, partial z is equal to minus 8 pi nu q over a naught. Okay. And so if we distribute this time derivative all throughout each term, what we get is partial squared q, partial t squared plus a naught over rho, partial squared p, partial t, partial z is equal to minus 8 pi nu over a naught, partial q, partial t. Okay. Right. All right. And so there's our two equations. Okay. And once again, you'll see that, because we took the time derivative of this, we end up with this cross derivative of p, right? So we have partial squared p, partial z, partial t on both equations, okay? And so what we can do now is we can use both equations here and eliminate that from the equations. Okay. Okay. So any questions on this so far before we jump into doing that? Okay. All right, and so the way that we're going to do that is we're going to multiply the conservation of mass equation by C naught squared and subtract it from the momentum equation. Okay. All right, and so let's take the conservation of mass equation and multiply by C naught squared, right? So we have C naught squared times A naught over rho C naught squared, partial squared P, partial Z, partial T, plus partial squared Q, partial Z squared is equal to 0, okay? And so if we multiply this through, then, the C naught here is going to cancel out. And then we have a C naught squared on the Q term, okay? Right, and so we end up with A naught divided by rho partial squared P, partial Z, partial t plus c naught squared partial squared q partial z squared, okay, is equal to 0. Okay. And then let's subtract the momentum equation. And so the momentum equation is partial squared q partial t squared, okay, plus a naught squared divided by, or a naught, sorry, just a naught divided by rho, partial squared p partial z partial t, okay, plus 8 pi nu divided by a naught, partial q partial t, okay, equals 0. All right. And so we're basically subtracting these two equations now, because what you'll see here is that on the first term, we have a naught over rho, partial squared p partial z partial t, right? And then on the second equation, we have the exact same thing. And so these guys are going to cancel out, okay? And then once we do that, and once we simplify, all that we're left with is the classical wave equation. Okay, so we have partial squared q partial t squared is equal to c naught squared partial squared q partial z squared minus 8 pi nu divided by a naught, okay, times partial q partial t. And so what we have here is the classic wave equation, which is a linear PDE. Okay. Right. And so this is nice right here because you know, the wave equation, you know, is one of those equations that that you learn to solve analytically through like a PDE's class, right? And so you know, we're not going to go over every single detail of you know, how to solve this, but you know, just know that you know, this is a an equation that's very traditionally solved by hand, right? And so this is good, okay? Because what we do know now that the equation's this form, we know what the solutions will look like. And then knowing what the solutions will look like will help us, you know, help us immensely with the derivation. Okay, so any questions on this? It's a lot of math, I know, but you know, it's you know, you know, the reason I kind of did that exercise was this is kind of one of the big conclusions here, right? You know, because we've been talking a lot up to this point of, you know, pressure wave propagation, you know, and you can see here, you know, why we call it a pressure wave, right? Because it follows the wave equation, right? And so, you know, that's why we don't call it like a pressure pulse or the pressure, you know, wiggly, or the pressure, you know, force or anything like that, right? It's literally called a pressure wave because it follows this wave equation, right? And so if you've seen this wave equation before, then you know you kind of know how it behaves. But if you haven't seen this wave equation before, then you know, just know that you know, all waves, you know, to some extent, you know, in kind of applied math and applied physics, kind of follow this equation, right? And so the fact that you know we were able to go, you know, from our 1D equations and then get something classical like this, you know, just kind of shows that, you know, we kind of understand a lot about how this actually behaves already, you know, because it follows this kind of, you know, this equation. Right? And so if you ever get a chance to, you know, take some applied math classes, you know, it's a really fascinating thing because, you know, when you take a lot of these like math classes, you learn about all of these kind of classical equations, like wave equation, things like Laplace equation, things like Poisson equation, things like that, right? Which you might think it's, you know, these are very specific kind of math problems that, you know, that don't have a lot of applications. But when you start to dig into, you know, a lot of the applications, you'll see that, you know, a lot of physical phenomenon in different fields, you know, be it like fluid mechanics, electrodynamics, heat transfer, structural mechanics, you know, a lot of them disturbingly kind of fall within the same patterns of different equations, right? And so there's kind of a reason why, equations like this kind of become famous, is because a lot of physics and a lot of, a lot of physical phenomenon, fall into these equations. They're not all exactly the same, but, they have a lot of the same trends, right? And so, it's kind of a eureka moment when you're doing these kind of, heavy derivations with, the physical problem, and you get kind of a classical math problem out of that, because, you kind of know how to solve that classical math problem. Okay. All right. And so in particular for this one, we have a classical wave equation. And so we kind of know what these solutions look like. Right? Okay. And so for the classical wave equation, we know that the solution is both separable and also periodic in time. Okay. And so basically what that means is that our solution looks like this, right? Right. And so our solution is going to depend both on z and t, okay? Right. And so it's going to be the product between these two things. And so it's going to be the product of some amplitude function p1 of z, okay? And it's going to be multiplying by e to the I omega t, okay? And then our flow solution is going to look the same thing, right? So we have q of z and t is equal to q1 of z times e to the I omega t, right? Where remember, e to the I omega t is a very special function, which is, Euler's function here. And it's kind of the most generic kind of sinusoidal function, right? And so e to the I omega t is going to be cosine of omega t plus I sine of omega t, okay? And so, since we can't choose between sine and cosine, we just, we just kind of say it can be both, right? It'll make our math actually a little bit simpler too, okay? All right, and so now that we've kind of assumed a form of the solution, let's take this and plug it back in to our wave equation. All right, and so we do that, we end up with the following. And so we have, first we have partial squared q partial t squared. And so that's going to be partial squared partial t squared of our expression here for q. And so it's going to be q1 of z times e to the I omega t, okay? This is equal to c naught squared times the second derivative with respect to z, so partial squared partial z squared of q1 of z e to the I omega t, right, minus 8 pi nu over a naught times partial partial z of q1 of z e to the I omega t, okay? All right. And so now what we can do at this point is we can carry out these derivatives, which is fairly simple to do because our situation was separable, okay? Okay. And then we're going to end up with a, with an evolution equation to solve q1 of z, okay? All right, but we'll continue on that on the next page. And so are there any questions on this so far? Okay. Oh, I think this should be a t derivative actually. Okay. And so that last term there should have a derivative with respect to t, not z. So I think there's a typo in my notes on that. Okay. Okay. And so if we carry out the derivatives, this is what we get, right? And so we, for the first term, we take the second derivative with respect to time. Oh, yes. Mm-hmm. Yep. Mm-hmm. All right, and so we take the derivative of that first term with respect to t twice. And so what comes out of that is I omega squared. And so the I squared becomes a -1. And so we have a minus omega squared Q1 of z e to the I omega t. Right? For the next term, we just have C naught squared d squared q dz squared, okay, e to the I omega t, right, minus 8 pi nu divided by rho, or divided by a naught, sorry, times I omega q1 of z e to the I omega t, okay? All right. And so here our choice of using the exponential term pays off because, you know, all these terms are going to cancel out, okay? And then what we're going to do here is we're going to solve, you know, kind of group the terms together, okay? Okay, because you can see here we have two terms with q1 of z, right? And so what we end up with is d squared q dz squared plus, or minus, sorry, minus 1 over c naught squared. Right? So I also divide the entire thing by c naught squared times I omega, 8 pi nu divided by a naught minus omega naught squared q1 of z, okay, it's equal to 0. Okay. This is a good time to make a change of variables or define a new one because this is kind of a big cumbersome term here, okay? And so let's take this giant term here and let's define it as lambda squared. Okay. So lambda squared is going to be 1 over c naught squared times I omega 8 pi nu divided by a naught minus omega squared. Okay. And if we make that substitution, you know, and noting that this guy right here is a constant, then we end up with the following ordinary differential equation, right? And so we end up with d squared q dz squared minus lambda squared q of z is equal to 0. Okay. Right. And this is nice right here because you know what this is just a regular ass ODE, right? And so we don't have any partial derivatives anymore. We just have an ordinary differential equation, which we know how to solve this. Okay. Okay. And so this is nice because this has a very, very simple solution in terms of ODEs. Okay. Okay. So any questions on the steps that I went over on this page? It is just a regular ass ODE, and so this, you know, this whole process kind of reminds me of this scene, and I think it's from Kung Fu Hustle. If you guys have seen that movie, where like the guy you know, he wants to kind of show how tough he is to this new village. And so he's trying to pick a fight with some of the villagers, and he picks people that he thinks look really weak, but then they're actually like really buff. And so finally he picks on like this little kid. He's like, come here, little kid. And then he beats him up. Yeah, such a good movie. I love that movie. And so this is kind of the same thing. And so, you know, we started out with some really intimidating equations, and we kind of, you know, did a lot of tricks and stuff like that. And now we end up with something that we can solve. It's like, all right, now we can solve this guy. Yeah. All right. Our question. So once we solve, we plug in the lambda's value. Yes. Yeah. So the lambda's value, and you'll see that, you know, once we get to the algorithm later on, that, you know, this is not a process that you would do by hand. And so this is very much, you know, designed kind of like everything in this class, designed to be more like a computer algorithm, right? And so I make a lot of these variable substitutions here, not, you know, not to confuse you guys, but more just to kind of make it easier to go back in and code it later. Because what you can easily do in MATLAB is say you can define this variable lambda as a MATLAB variable and just kind of plug in the values from that. Yeah, I think the kid beat him up too. Yeah. It's been, now I want to rewatch the movie because it's so good. Yeah. But yeah, so, you know, because this is kind of a computer algorithm, you know, I'm defining kind of all these variables, and we're making all these substitutions because later on, once you're writing the program, you know, defining a new variable was really easy in MATLAB. And so you just say that, you know, new variable is equal to this, and then now the rest of your math is kind of really, really simple. And so, you know, I know because you know, I've been there too, that when we're doing these derivations, and when we make all these substitutions, and, you know, it makes things really hard to follow because you're trying to keep track in your mind about, you know, of all these like 20 different variables, and, you know, and it's hard, you know, and I know that, you know, a lot of you guys are probably sitting through this lecture right now and saying, you know, what's lambda, what's a naught, what's omega, you know, and that's normal. And so, you know, but, you know, hopefully that, you know, when you kind of go back through and kind of watch this lecture again and kind of do the homework, that, you know, you'll see that once you develop the code, a lot of it's just kind of plugging in and say, all right, this variable goes here, that variable goes there. And we can kind of work with it from that perspective. Yeah. Okay. But now that we have the ODE in this form, we can go ahead and solve for the solution because it's fairly simple to do, right? And so the solution to this ODE, you know, if you kind of look back on your notes from like 308 or from Math 250A or 250B, I'm not sure which one it is, right? And so we end up with a solution that looks like this. Right, so we have C1 e to the minus lambda z plus C2 e to the lambda z. Right, and so fairly simple. Okay, and so that's nice. And so this is the solution for Q. But, you know, we're not only interested in Q, we're also interested in solving for P as well. Okay. And so what we can do is now that we have this kind of closed form expression for Q, we can plug this back into our conservation of mass to get an expression for P. Okay. And so if you remember, our conservation of mass expression is A naught divided by rho C naught squared, partial P partial T, plus partial Q partial Z. Okay. That's equal to 0. Okay. All right. And so what we can do from here is we can plug in for both P and for Q. Okay. Right. Because remember, P had a very similar form as Q, except, you know, the amplitude out in front was different, right? And so we plug in for that, and what we get is A naught rho C naught squared partial T of P1 of Z e to the I omega T, right? Plus partial Z of Q1 of Z times e to the I omega t, okay? Right, but we have Q1 of z, so Q1 of z is just this guy up here, okay? And so let's go ahead and plug that in for that right there, okay? And what you'll see is that, you know, all the e to the I omega t's are going to cancel out again as well, okay? Right. And so just because I want to reach kind of a good stopping point for today's lecture, you know, I'm going to kind of refer you to the notes because most of the steps are there. But we end up with kind of a very similar expression for P, right? And so if we work through this and solve for P1 of Z, what we get is P1 of Z is equal to minus rho C naught squared lambda divided by I omega A naught, okay, times minus C1 e to the minus lambda Z plus C2 e to the lambda Z. Okay. Right. And so it looks very similar to our Q here, except, you know, we have that different constant out in front. Okay. But the key thing to note here is that both Q and P depend on these constants C1 and C2, right? And so we haven't solved for these yet. And so remember, the way that we usually solve for these, that we apply boundary conditions, okay? But it's comforting to note that both our function for Q and for P depends on the exact same C1 and C2, okay? And so the next part of the math here is that we're going to solve for C1 and C2 by applying boundary conditions. And once we solve for C1 and C2, then we have basically our expression for P pressure and for flow. Okay. All right. So any questions on this so far? Okay. All right. And so let's go ahead and start working on that. Okay. All right. And so in order to apply boundary conditions, we have to have a boundary to look at, right? And so let's consider kind of a generic vessel for this. Okay. And so our generic vessel will look like this. Okay. And so on one hand, we have the inlet, and the other side, we have the outlet, right? So we're going to assume the flow goes from left to right, right? And this side of the vessel, we're going to define it as Z is equal to 0. And the other side, we'll define it as Z is equal to L, right? And so this vessel has kind of a length of L. Right? And so what we're going to do is we're going to define the basically the conditions at the inlet and outlet of this vessel. All right. And so first, let's define the condition at the inlet. And at the inlet, we'll assume that the flow rate is known. Okay. Okay. And so the way that we can define that is we say that Q1 of 0, so Q1 of Z is equal to 0, we'll assume that this is Q naught, okay, where Q naught is something that's going to be known. Okay. All right. And at the outlet, we're going to assume that the impedance is known. Okay. And so remember, impedance is kind of the same thing as a resistance. And so, if you kind of compare this to our 3D CFD simulations, remember for those 3D CFD, we define the resistance at the outlets of the model, right? And so this is kind of the same thing, but instead of assuming resistance, we're going to assume impedance, okay? And so mathematically, it looks kind of like this. Oh, it should be P1 of L, sorry. P1 of L minus ZT times Q1 of L is equal to 0. Where this ZT right here, this ZT is our what's called terminal impedance. Right. And so it's a measure of basically how much the how much resistance to flow is kind of downstream of this vessel, as a function of frequency. Okay. All right, and so what we can do now is we can apply these boundary conditions to both Q and P, and use that to solve for C1 and C2. Okay. Okay. So any questions on this? Yep. All right, question. So this resistance has more to do with the geometry as opposed to resistance from viscosity. So it's a bit of both. And so the amount of resistance that you get due to viscosity does also strongly depend on the geometry as well. But I think the difference here is that our original viscous resistance, that really only depended on just the that really only depended on the radius of the vessel. The length kind of played into account too, but kind of very minorly. And so with impedance, we're also, the length and the radius are also still going to be important, but also kind of the configuration of the vessels that you'll see is also going to be important as well. Yeah, they are very analogous though, and they both depend on geometry and viscosity. Okay. So let's go ahead and apply these boundary conditions and then use those to solve for the constants. Okay. All right. And so let's apply boundary condition 1. Okay. Right. And so boundary condition 1 states that Q of 0 is equal to Q naught. Okay. And so let's take our expression for Q1 and plug in Z is equal to 0. Right? And so Q1, remember, is C1 e to the minus lambda times Z, but we'll plug in 0, plus C2 e to the lambda times Z, which is 0. Okay. Right? And so both of these are going to cancel, or they're just going to equal 1. Okay. And so our first equation is that Q0 is equal to C1 plus C2. Okay. Right. So nice and easy for that. But we can't really do anything more because we have one equation and two unknowns still, right? And so in order to solve for both C1 and C2, we have to apply both of the boundary conditions. Okay. All right. And so our other boundary condition was our output 1. Okay. And so our output 1 says that P1 of L minus ZT Q1 of L is equal to 0. Okay. And so into this, let's plug in P1 of L and Q of L, Q1 of L. Okay. And so P1 of L, it looks like the following. So P1 of L is equal to minus rho C naught squared lambda divided by I omega A naught, right, times minus C1 e to the minus lambda L plus C2 e to the lambda L. Okay. And then Q1 of L is equal to C1 e to the minus lambda L plus C2 e to the lambda L. Okay. All right. And then what we can do is we can plug these expressions into our boundary condition here. Okay. All right. And so before we do that, we're going to make another change of variables. And so, another variable that's introduced here. Okay. And so this guy, since it's kind of a combination of a lot of different constants, let's call this variable, we'll call it z naught. Okay. And so we'll define z naught to be positive rho c naught squared times lambda divided by I omega a naught. Just to make our lives just a little bit easier when we're plugging this in. Okay. And this z naught here has a very specific name because it's going to come into play later, and so this is known as the characteristic impedance. Okay. Right. And so the characteristic impedance, you can kind of think of it as the impedance of this particular vessel, right? Just like, we've kind of said before that, resistance, you can find the resistance of a particular vessel segment. The characteristic impedance represents the impedance of this particular segment, right? And so if we have a vessel that looks like this, right? Okay, and we're wondering, what's the impedance of this vessel segment, right? That impedance is going to be Z naught. Okay. And so basically by the flow passing through this vessel, it experiences a impedance of Z naught. Okay. And so that's different from ZT, right? And so we're starting to have two different Z values here, right? And so remember, ZT is the impedance of everything that's downstream of this vessel. Okay. Because remember, when we're analyzing these blood vessels, we're not just looking at just this vessel in particular, but the flow in this vessel is going to depend on everything kind of downstream from this as well, right? And so if you think of it, let's say that there's a bifurcation here. The terminal impedance or ZT of this vessel is a combination of the characteristic impedances of all those downstream vessels. Okay. And so it's kind of a lot to wrap your head around now, but I think let me just kind of plant those ideas in your head right now, and then on Thursday, once we go over the algorithm, then we'll kind of draw further distinctions in between these terms. Okay. Okay. So any questions on this? All right, so we're almost there for today, and so let me just make a couple more points, and then we'll call it a day. Okay. And so by plugging all this in, plugging in for the characteristic impedance and also for the for the boundary condition, we end up with the following. Okay? So we have minus Z naught times minus C1 e to the minus lambda L plus C2 e to the lambda L, okay, is equal to ZT C1 e to the lambda minus lambda L plus C2 e to the lambda L, okay? And so if we rearrange these terms, and so let's organize in terms of let's see, one exponential term and the other one, then what we get is Z naught minus ZT times C1 e to the minus lambda L minus Z naught plus ZT C2 e to the lambda L, okay? That's equal to 0, right? Okay. And then what we're going to do is we're going to define another variable, right? I know we're doing a variable overload here, right? And this variable is actually significant. And so, remember when we started this lecture today, we talked about how wave reflection can occur whenever you have changes of impedance, between different vessels, right? And so this variable is going to reflect that. And so this variable, which we call capital gamma, this is called the reflection coefficient. And this is equal to the following. So it's going to be equal to Z naught minus ZT divided by Z naught plus ZT. Okay. Right. Right. And so what this represents, and this is a coefficient. So this ranges between 0 and 1. Okay. And so the value of this coefficient will tell you how much of the pressure wave is going to reflect at the end of this vessel. And so if you have a reflection coefficient of 0, and so basically the characteristic impedance and the terminal impedance, they match, then you have no wave reflection. And so, the wave just kind of passes through. And then the opposite of this is if you have a reflection coefficient of 1, then you have complete reflection. And so the wave hits, and then all of it comes back at the same time, right? And then there's also everything in between where, there's some part of the wave will pass through, and some of it will reflect back, and that's all determined by this reflection coefficient. Okay. All right, and so any final questions on this today? All right. All right, so thank you guys for tuning in today. I know there was a lot of math today and a lot of variables, but on Thursday, we'll kind of clean all this up, and we'll talk about the algorithm, and we'll talk about how you do the homework for this as well. Right? So thank you guys for tuning in today. Hope you guys have a good rest of your evening, and I'll see you guys on Thursday.
Thank you, Professor.
Thanks, guys.
Hi, Professor.
Yep.
I have a question about my software. So may I share my screen?
Yep. Oh, yeah. Okay. Yeah, go for it.